Good morning. All right, so we're going to pick up where we left off yesterday. This is still section 4.5, so we got a few more examples to finish up there. This will probably take us all of today, and then that'll just leave us with 4.6 to finish up in this unit. And then sometime early next week, I'll post the test, and then you'll have about a week to get that done and submitted. So just know that that is coming up, but it'll be next week sometime when we get to that. Continue to work on homework. There was the one that was due last night, but now that we're going to finish up 4.5 today, probably that'll give you enough information to do about half of the upcoming homework on 4.5 and 4.6. And I'll adjust that due date as needed, if we don't get to everything, but go ahead and be working on that. So any questions about anything before we get started today? All right. So let's take a look at example 8 here. So we're trying to solve this equation for x, and we got natural log of x is equal to 8. So what do we know about this equation, and what might we be able to do to actually solve for x or get x by itself here? So tell me this, what is the base of the natural log? So not 10, right? Because the common log has a base of 10. So good, Sarah. So the natural log has a base of e. So what I'm going to do is I'm going to, even though it's understood, right, I'm going to rewrite this now with a base of e, just so it's clear that that's what our base needs to be this time. Now what we want to do is we want to try to rewrite this in exponential form. So how could I take that log form and rewrite it in exponential form? Good, right? E, we're going to raise it to the 8th power, and that should be equal to x, right? So we're going to have e to the 8th equals x, and we're done. Because now we have x equals e to the 8th power. That is our answer, and we're finished with that problem. Okay, so anytime you've got a log, right, where it's just a log by itself like that, the easiest way to solve these is just to switch it over to exponential form, and a lot of times that'll get our x by itself. Sometimes, and you'll see this on the next one, you have to do a little bit more work after you change it to exponential form, but that's always going to be your first step anytime there's just a single log to take care of. Any questions on that one? And if they ask you, like in WebAssign, for a decimal value, right, then just put e to the 8th in the calculator, round it off to however many decimal places they tell you, but e to the 8th is the exact value this time. All right, so how could we rewrite the second one here? Good, right? So we take the 2, which is the base, we raise it to the 3rd power. So we have 2 to the 3rd is equal to everything inside the log here, so 25 minus x. All right, so then what could we do to try to solve for x? Okay, so we could add the x, right? So if you want to do that, move it to the other side. 2 to the 3rd power. Good. So that's just going to give us x plus 8 over here is equal to 25. And then we could do what? Good. Subtract the 8. And what's 25 minus 8? Good. So x equals 17 this time. And just always keep in mind, you can always substitute these back in just to make sure they work, right? So if you plug the 17 in, that's 25 minus 17, that's 8. And that tells us that 2 to the third power equals 8, which is correct. Any questions on that one? All right. Let's take a look at this one now. All right, so similar to the last two that we did, we only have a single log that we're trying to solve for x, right? But to be able to do that, we actually need to get the logarithm by itself first. So what would we have to do first here if we want to try to get the log by itself? Good. So let's subtract the 4. Go ahead and move that to the other side. Now we've got 3 log 2x equals 16 minus 4 is 12. Okay. What should we do next? So you could make the 3 an exponent. What I'm going to tell you, though, is that's just going to overcomplicate things just because then you're going to have an x to the third power, and then we're going to have to end up taking a cube root at the end. Okay, so Naomi, that's going to be the easiest next step is just to go ahead and divide by the 3, right, to get rid of it in front of the log. So I'm just going to divide both sides of this equation now by 3. So that gives us log 2x equals 4. Okay. So Kenneth, technically moving the 3 to the exponent is mathematically correct, and it would technically work in the long run. It's just going to be more work for us, and so that's why I try to avoid it if we can. All right, so then what can we do? Good. So now we can rewrite it in exponent form. Remember here with a common log, the base is an understood 10. And so we're taking this base of 10, we're raising it to the 4th power, and that should be equal to 2x now. All right, so then what can we do? Okay, good. So we're going to take 10 to the 4th, we're going to divide by 2. What is 10 to the 4th, by the way? Good, 10,000, right? So 10,000 divided by 2 will give us what? 5,000. So there's our x. So again, anytime you just have a single log like that, first thing we want to do, isolate the logarithm, so move everything else to the other side first, then we can rewrite it in that exponential form, and that should give us our x value by itself. Any questions on that one now? All right, let's take a look at this one. And notice here it says algebraically and graph. We'll do it algebraically first. We'll get our solution, and then we'll look at the graph just to check our answer. All right, now this time we do have multiple logs. So what do you think we might want to do first here to get this problem started? Good. We want to combine the logs into a single log, and then we can, go from there just like we have on the previous problems. So how would I combine these logs? Multiplication. Good. All right, so we're going to take log of x plus 2 times x minus 1. Because again, anytime you have addition of two logs, as long as they have the same base, we can combine them using multiplication. And that's still going to be equal to 1 now. Once we've combined those, now we have that single logarithm. What can we do from there? Okay, good. So let's rewrite it in exponential form. So what would the exponential form look like this time? Good. So it's going to be 10 to the first power, right? Because again, the base here, it's a common log of 10. So 10 to the first is equal to x plus 2 times x minus 1. So now we've gotten rid of our logarithm. So now if I want to solve for x, what are we going to have to do from there? Good. So let's go ahead and multiply out what we have on the right-hand side. So 10 to the first is just 10, right? Over here now, if we FOIL, we have x times x, x squared. We're going to have a minus x for the outer terms, a plus 2x for the inner terms. So that's going to be a positive x. And then 2 times negative 1 is going to be negative 2. All right, now, once we've multiplied all that out, then we can do what? Good. Move the 10 to the other side because we need this equal to 0 to be able to solve for x since we have a quadratic. We're going to have x squared plus x minus 12. Right, and now once we've set that quadratic equal to 0, now we can do what? Good. Now we need to try to factor if possible. And again, if factoring doesn't work, we always have quadratic formula to fall back on. Let's see if this factors. Do our two sets of parentheses. And so what are the factors going to be for that quadratic? Good. So we need a 4 and a 3, right, to give us the 12. We need an x and an x to give us the x squared. And so what are the signs going to have to be this time? Good. The 3 is going to need to be negative, and then our 4 need to be positive, and that way we get a negative 12 when we multiply, but we also get a positive x once we add those together. All right. And once we have those factors, now we can do what? Good. So equal to 0. So we're going to have x plus 4 equals 0. We're going to have x minus 3 equals 0. And so over here, we're going to get x equals negative 4. And the other one's going to give us x equals positive 3. Questions so far there? All right, let's take a look at the graph. And then we're going to come back to the algebra here. I want to look at the graph first. All right, so log of x plus 2 plus log of x minus 1 equals 1 Okay, just in my standard window, right, that's what I see. Now, what did we say our solution should be here? -4 and +3, right? Now, looking at the graph, what does it look like the solution should be? Just 3, right? Because if we're looking for the solutions to this now, we'd be looking at where does it actually cross over the x-axis. And in this case, it only crosses the x-axis at 3, right? And you could zoom out to make sure it doesn't cross anywhere else. But the fact that we got a -4 and it doesn't cross at -4, that should key us in that there's something going on there. So let's go back and look at our algebra again. Let's think about why the graph doesn't actually cross at -4. So let's take the 3 and substitute it in and see what happens, right? So if I do that with the 3, I'm going to end up with the log of 3 plus 2 is 5, plus the log of 3 minus 1 is 2 equals 1. Okay, and we're checking to make sure this actually works, right? Well, we have addition, which means we can use multiplication. So that's going to give us the log. 5 times 2 is going to give us 10 equals 1. And now the base of this log is a 10. And so this says that 10 to the first power equals 10, which is a true statement, right? So that's why our graph does cross at 3, right? And 3 is a solution to this problem. Now let's check the -4. If I substitute in the -4, I'm going to have log of -4 plus 2 is -2, plus the log of -4 minus 1 is -5 equals 1, right? What's wrong with that? You can't take the log of a negative value, right? And so as soon as we end up with those negative values inside the log here, we automatically have to say, okay, we can't do that. That's not going to work. And so this solution right here does not work. Right? So that's why it's so important either to use the graph to kind of check yourself, or at least go back and plug in your values and make sure you don't end up with any negatives inside your log. Now, the one thing I'm going to tell you to be careful of, don't just assume that all negative answers don't work, and don't assume that all positive answers do work, because it's after we substitute them in that we can't have a negative in there. So it's possible that when I plug in the -4, if I'm adding large numbers in both, then I'm actually going to end up with positives and I'm fine. It's also possible that if I have a 3 and I'm subtracting big enough numbers from the 3, I could still end up with negatives inside the log. Okay, so that's why we have to go back, plug them in, and check to make sure you don't have any negatives inside your logs. And as long as you don't, then those solutions should work. But if you ever get a negative inside of a log, you know that solution is not going to work. Okay? Any questions on that one? And in general, the only ones we really need to worry about checking really are the ones where we have multiple logs to begin with and we've combined, because it's in that process of combining and multiplying that those negatives, because a negative times a negative will become positive. So it looks like that actually works, but the problem is we can't have a negative in there to begin with. So again, you start combining the logs that you really need to go back and double check your solutions. Anybody need more time on that one now? All right. Let's take a look at this one. All right. So if we wanted to solve this for x, what do you think we might need to do first here? Okay, so we could try making the 2 an exponent, right? In this case, though, it's similar to that other one that I was talking about. Rather than moving those numbers into the exponent, if we're just trying to get the log by itself to begin with, it's probably going to be easier just to divide both sides by the 2, right? So just move the 2 to the other side. Let's try that. So I'm going to divide both sides by the 2. I've got x squared over 2 equals the natural log of x plus 2. Okay, so just like all the other ones, right? If we can isolate the logarithm first, then what could we do from there? Good. So now we can rewrite it in exponential form. We know our base of a natural log is going to be an e, right? So this would become e to the x squared over 2 power equals x plus 2. Okay, now what? Okay, if we subtract the 2, that's us e to the x squared over 2 minus 2 equals x. What's wrong with that? There's still an x on the left-hand side too, right? Okay, and so if I wanted to try to get it by itself now, what's going to end up happening is I'm going to all those steps in reverse, and I'm going to end up right back where I started, right? So there's no good algebraic way to do this problem, mainly because I have this x to begin with and this x inside of a log. So whenever there's an x outside of a log and an x inside of a log, and you're trying to solve for x, algebraically, there's just not going to be a good way to get x by itself. Okay. What we're going to have to do in this case is just graph it and see if we can find the solution that way. So that's what I'm going to do is I'm going to go to Desmos. I'm going to graph this equation. I'll share this with you. All right, so there's what the graph looks like for x squared equal 2 times the natural log of x plus 2. And so what are we looking for then if I'm looking for my solutions? Okay, good. We need to find out where the x-intercepts are, right? Where does it cross the x-axis? And so again, in Desmos, that's pretty easy to do just by clicking on those points. Well, I say that, but for some reason it's not allowing me to do that. All right, I'm going to try this other graph. Not working. Hang on. Let me refresh this. Try that again. So did anybody get that? So I did, yeah, I tried clicking on the equation and it's still just not giving me the option right now. So I might just need to update my browser or something because for some reason it's not giving me those points. Did anybody get the points for the x-intercepts though? Was anybody able to do that? So it should be, let me pull my work back up. If it allows you to actually click on the points, we should get these two values down here. So x equals negative 0.71, and then x equals 1.60. So Sarah says it's not letting her do it either. So yeah, so maybe there's just something wrong with Desmos right now. So I'll play around with it and see if I can figure out what's going on. Yeah, normally you should just be up on those x-intercepts and it should give you the answer. So they may just have something wrong with Desmos right now. Yeah. So I'll let you know what I find out there. But yeah, because x-intercepts, mins and maxes, things like that, usually those points are just available and you can click on them. If not, though, if you have your graphing calculator, you can always just go to second trace and do your zeros, left bound, right bound, to get those values that way using your calculator also. Any questions on that one, though? Like I said, anytime you have an X inside and outside log, okay, that's kind of the only way you're going to be able to solve that. Okay. Yeah, Sarah.
Why did you enter it on Desmos as x squared instead of ex squared divided by 2? My video cut out, so I didn't hear the reason for that.
So I just went all the way back to the original equation, right? This said x squared equals 2 natural log of x plus 2. So you could enter either one of those, right? Because the work that we've done all the way up to e to the x squared over 2 equals x plus 2, we could have entered that equation too because they're equivalent. But I just went back to the original and just put the original equation in. Does that answer your question? I think I left out the 2, though. Maybe not. I can't remember. But either way, right, as long as you put in that original equation, that's what we're trying to solve. Other questions there? All right. All right, word problem here, but they give us a formula to work with. So it says if I sub 0 and I denote the intensity of light before and after going through a material, and x is our distance in feet the light travels in the material, then according to the Beer-Lambert law, we have this formula right here. Now, K is just going to be some constant that depends on the material, right? So basically, you're going to have some materials that allow a lot more light through and some materials that let very little light through. Okay, so that's what that K is going to be based off of. It says we want to solve the equation for I, and then once we've done that, we're going to use the values in the bottom part to actually find our light intensity at a depth of 20 feet. Okay, so if I want to take that formula and solve for I, what would we need to do first? Okay, good. So we want to move the negative 1 over k to the other side. Let me put in just a blank slide right here, and I'm going to copy that equation. All right. So we had -1/k natural log I over I sub 0 equals x. Okay, and so we want to move the -1/k to the other side. So Kenneth said divide by -1/k. That's the same thing as doing what? What other operation could we do there that would also get rid of that k and the -1? Yeah, we're just multiplying, right? Because divided by a fraction, same thing as multiplying by the reciprocal. So I'm just going to multiply this now by -k, because that would be the reciprocal of -1/k. I'm going to multiply both sides here by -k. So that gives me natural log I over I sub 0 equals -kx. All right, now what could we do? Good. Write it in exponential form. So we know our base here for the natural log is going to be an e. So we have e to the -kx is equal to I divided by I sub 0. And we're trying to solve for the I, and so what are we going to have to do now? Okay, so multiply by I0, right? So times I sub 0 on both sides. So now we have I sub 0 times e to the -kx equals I. So there's our work to actually solve for I, which represents our intensity of light. Any questions on the steps to do that? All right. So now that we've got that, I'm going to go back to the previous slide. Okay, and it says for a certain lake, our K value is going to be 0.025. The light intensity is I sub 0 equals 14. So that's the initial amount of intensity in our light. We want to find the new light intensity at a depth of 20 feet. So now we have our K value, 0.025. We have our initial intensity, 14, and our depth, which is going to be represented by which variable? X, right? Because that was measured in feet. So there's our X value. So we have a K, we have an I sub 0, we have an X, and we're trying to solve for I. So we're just going to plug all of those numbers into the formula that we just got. Okay, so I'm going to go back to the other slide. We're going to start plugging those in. So what was my I sub 0? Okay, so that's 14. Good. I'm going to put 14. E. What was our K value? 0.025. And so in this case, it's a negative K, so we have to make it negative 0.025 times X. Was our X value? $20 feet, right? So we're going to put 20 in place of the X. And at that point, now we can just put all of that right into our calculator and actually get a value. And so if we do that, and 2 decimal places should be sufficient here. All right, so 8.49 is correct. So what that tells us is if we have an initial intensity of light of 14 lumens at a depth of 20 feet now in this specific material, right? So we have like a lake here, right? So the light's trying to travel through the water. Once you go down to 20 feet, our light is a lot less intense, right? It's down to 8.49 lumens now. And so the deeper and deeper you go, the less and less light there's going to be, right? Because it gets distilled as you go further and further in depth, okay? So that's what that formula is doing for us. It's telling us if you have an initial light intensity of something, once you go a certain distance, a certain material, right, what's the new light intensity going to be? How bright is it actually going to be at that point? Any questions on that one? All right. All right, so now we're going to look at some money again. Okay, so we have a sum of $5,000 being invested at an interest rate of 5% per year. We're going to find the time required for the money to double if our interest is compounded according to the following methods. Okay, and so we're going to do this twice because we're going to do it semi-annually, and then we're going to do it again for continuously. All right, so let's just review our formulas first. So if I'm doing semi-annually, what's the formula going to be that we're going to use this time? Okay, good. So it's the compound interest formula, and specifically, it's the first one we looked at back in 4.1, right? Because this is semi-annually now, so we actually do have an n value. So remember, our formula was A of t equals p times 1 plus r over n to the n power. Okay? So now let's think about what information we're given. So what's one thing that we know? Good. So our P, our principal, is going to be 5,000. That's the amount we're investing. So I'm going to put 5,000 in place of the P. 1 plus. What else do we know? Okay, the R value is 5%, so we convert that to a decimal. Good. So that's going to be 0.05. Okay, and what else do we know? Okay, do we know the value? Okay, we know the n, right? So 2 for semi-annually, that's going to be the n value in this case. So that's going to go right here. So we're going to have a 2 there, and we're also going to have a 2 up here. But time is what we're looking for, right? We're trying to find the amount of time that's required, okay, for our money to double. So we're almost there, right? So we've got our principal, we've got our rate, we've got our end value. So if I'm looking for time, what else do I need to know? So we know principal. Principal was 5,000. So we're still missing. Right. We need the amount on the other side, but we know that we want to double our investment. So if we start with 5,000, we're going to need to end up with 10,000. So I can put 10,000 on the left-hand side now. Okay, so even though they don't give us a specific amount, since we want to double our investment, we can just take the 5,000, double it, and that gives us how much we want to end up with. So now we've got numbers in place of everything except for T. We need to solve for time. What would we have to do first here if we're trying to get T by itself? Good. Let's divide by the 5,000. Go ahead and move that to the other side. And so what's 10,000 divided by 5,000? 2, right? So we're just going to have 2 over here. Now on the other side, we can go ahead and start cleaning up what we've got. So we have the 1 plus 0.05 divided by 2. So what's 1 plus 0.05 divided by 2 going to give us? Good. 1.025 to the 2t power. All right. Now, I'm trying to solve for t. What are we going to have to do next? Put it in log form, right? Because in this case, if you're ever trying to solve for a variable that's in the exponent, we need to take the log to be able to met exponent out front. So what type of log would you like to use here? Natural log, that's fine, right? And in this case, it really doesn't matter. We don't have any e's. We don't have bases of 10 either, right? So either one would be fine. So I'll take the natural log of both sides. And once I've done the natural log on both sides, now we can do what? Okay, so not exponential form, right? Because we only want to go to exponential form if we have a single logarithm. We took the natural log on both sides in order to do what? Why did we have to do that? Bring out the 2t, right? So we want to take the exponent now, we want to bring it out front. So I'm going to have natural log of 2 equals 2t times the natural log of 1.025. So yeah, anytime you have a variable in an exponent, take the log on both sides, and then the next step is going to be to bring that exponent out front. So now we're almost there. We want to get t by itself, so what are we going to have to do now? Good. Divide. What are we going to divide both sides by, though? Okay, we need to divide by the natural log. We need to divide by what? Yeah, the natural log of 1.025, right? So that whole thing. But what else needs to move? 2, right? So I'm going to divide by the 2 and the natural log of 1.025 on both sides here. Okay, and that way I cancel out the 2 and I cancel out that natural log of 1.025, and that's going to leave me with just t. Now at that point, now we can just go to our calculator because we want an actual t value. Just make sure when you put it in there, we need to make sure the entire denominator is grouped together here. Okay, so just make sure you have that. Okay, and let's go with 2 decimal places this time. Okay, so 1404 is correct. 14.04. Now, what are those units going to be? Years. Good. So just remember with these formulas, our time always going to be in years. So just over 14 years for our money to double at that interest rate. Any questions on any of those steps? All right, so let's see if we can do the compounded continuously one. All right, so what's our formula for compounded continuously, first of all? Yeah, so P times E to the RT power, right? So now let's think about what we know, right? Because all the information from the previous problem is going to be the same. So what's one thing we already know? Okay, we know the principal, that was 5,000, so we can put that in there. E is just E, right? We also know the rate, that was 0.05, so that's not going to change. We're still looking for time. And what's our A going to be this time? 10,000 again, right? Because we still want the money to double. We're still going to have 10,000 on that side. All right, so now let's think about how we can get T by itself. So what are we going to do first? Divide by the 5,000 again. We already know that's going to give us 2 over here equals E to the 0.05 T. All right, so then if we're trying to solve for T, what are we going to have to do next? Natural log, good. And in this case, you definitely would want to use a natural log just because our base is E. So I'm going to take the natural log of 2. I'm going to take the natural log of E to the 0.05 T. So then what can we do from there? Good. The natural log and E cancel, and so that's just going to give us what's in the exponent over there. So we're going to have natural log of 2 is just equal to 0.05 T. And that's just one of those properties of our natural logs that tells us if we have the natural log of E to some power, we can just bring down the power. Natural log of E becomes 1. And now if we're trying to get T by itself, what do we have to do? Just divide by the 0.05, and then we can go to our calculator. And so what does that give us if we put that into the calculator now? Again, 2 decimal places is fine. So make sure that you're closing your parentheses after the natural log of 2 there. Okay, so 13.86 is what I got. Good, and then don't forget it's here. So this should be years. All right. Anybody not able to get that value now? All right, so just notice here, compounding continuously got us there a little bit faster, right? Because we got 14.04 if we were doing it semi-annually, 13.86 years if we're doing it continuously. Still close to 14 years either way, right? But slightly faster if we compound continuously. All right, so that's all I got for today. We will pick up tomorrow with section 4.6. Again, you can go ahead and start on the homework for 4.5 and 4.6. We've done everything from section 4.5 now. Let me know if you got questions, but otherwise, I will see you tomorrow. Have a good afternoon.